Good morning, everyone. Welcome back for our final class of mathematics. Well, with me, anyways. So, since I haven't actually received any questions from you guys from the previous chapters, I guess we will start a new chapter today. So, let's do vectors. So, those of you who have done further math, this is actually just a small fraction of what you have done. So if you're feeling good with further math vectors, you can probably skip this class and you would just be you'll be fine as well. But those of you who haven't done further math, we would be extending on what you know in AddMath. So in AddMath, we have done a bit of 2D vectors, right? So we're gonna do 3D vectors, specifically lines in 3 dimensions. And yeah, then we do the cross, no, we won't do the cross product, but we'll do the dot product. Yes. I'm not sure if we can actually cover the entirety of this chapter, but I'll try my best to do so. Also, I'm going to export all the classes that we've had to YouTube, and eventually I'll sort them out and I'll put them on a playlist so you can review these classes at your own time, because the videos on Twitch, they expire after 2 weeks. So if you want to watch any videos older than that, you're not going to find them. So I will most likely sort out the videos next week when I have a bit more time on my hands. Okay, let's get started. Right, so if you have a... how should I explain this? Let me start from... let's say you have a Cartesian plane and you have a point on the Cartesian plane. We'll call this point 2, 1. Okay, so 2, 1 is the coordinate of the point. But if I were to draw a line from the origin to the point, and I label this with an arrow like that, let's say we'll call this origin O, and this 2, 1 coordinate, we'll call it A. So from O to A, how do I go from O to A? I have to go 2 in the X direction. So 2 in the X direction and 1 in the Y direction. So usually the X direction, we denote that with an I and a curly thingy. And then for the Y direction, we use J. And that's just a convention. Another way of writing this is to write this as a 2 by 1 column matrix. So you just write 2, 1. Okay? So this is what we call a position vector. So if you have a vector, or basically sort of like a line with an arrow that starts from the origin, we call it the position vector of A. In this case, because our coordinate is A. Right? So let's say if we have another point here, let's say we call it B. This point is, maybe 1, 3. Then the position vector of B is going to be 1, 3. Okay? Now, suppose I want to draw a line connecting A to B. So if I start at A and I want to go to B, how do I do that? Well, I have to go 1 in the negative X direction and 2 in the positive Y direction to get to B from A, right? So AB, as A to B, I have to go 2 in the negative X direction. 1 in the negative X direction and 2 in the positive Y direction. So this is what you expect to get if you were to work out what AB is. So is there another way of doing this? Yes, there is. If you've done a bit of add math, you should remember this. So if I have AB, another way of going from A to B is to go from A to O first, and then you go from O to B. Okay, so this just means go to O first, and then from O you go to B. So do we have AO? We do not. We only have OA. But we can actually flip this so that this becomes OA by introducing a negative sign in front. Okay, for example, if I have a vector like this, and this is vector OA, if I draw it like that, this will be negative OA. So the negative sign just flips the direction of the vector to the opposite direction. Okay? So what is OA? Well, OA is 2, 1. What is OB? OB is 1, 3. So if you have a negative out here, you can actually put a negative inside like so. And when you add vectors, the top one, you add it with the top one, the bottom one, you add it with the bottom one. So you get -1 and 2. And as you can see, that's what you get, right? So another way of writing vectors is instead of writing OA, sometimes in the textbooks you see that they would write it as A, and then they just put a curly thing down there to denote that it's a vector. So instead of writing OB, they would write B. Okay? And AB, there's no specific convention for it, but you can assign it any number you want. So you can even call, you can call AB C, whatever. Just put an unknown, right? But typically for position vectors, the unknown that you use is a small letter of whatever alphabet that you use over here. So if it's OA, you put A. If it's OB, you put B. If it's OC, you put C, small letter C. So that's the convention, okay? You don't have to follow the convention. This is just what they usually do. Okay. So next up, we're going to look at subtraction of vectors and what they actually mean. So when you have two vectors and you add them up, you just add up the corresponding elements of the matrix, right? But what does that actually mean physically in the real world? So a vector is essentially a quantity with a magnitude and a direction. An example of that is the force in physics, not Star Wars, right? So let's say you have a box, right? And you're looking down from the box from above, and I push the box with this magnitude of force and then another force like this. So what happens to the box then if you push it from both sides like that? You would expect the box to move in this direction, right? So your resultant force should be this guy over here. So when you add vectors, so let's say we call this vector A, we call this vector B, and this is vector C. If I have vector A and I add it with vector B, I should put it like this. And this is vector B, and then C would be this one. Okay. So vector A could be something like 2, 0, and then vector B could be something like 0, 3. All right. So what is C going to be? Well, C is actually A plus B. So A is 2, 0 plus B is 0, 3. So you get 2, 3. There you go. Let me just change these values a bit real quick just to make things a bit easier to calculate. Call this 4 instead. right? So your vector C would have a direction 4, 3. So 4 in the x direction, 3 in the y direction. So your C would be pointing this way. Okay. So anyway, how do I find the magnitude of a vector? So the magnitude of a vector is the same as the length of a vector. Magnitude of a vector is the same as the length of a vector. So if you look at this guy here, if I want to find the magnitude of C, you can see that this is simply, a right-angled triangle. So you can use Pythagoras theorem, the Pythagorean theorem, to do, C is the magnitude of C. Usually we put the modulus to denote the magnitude. The modulus doesn't mean take the positive value. In the case of vectors, it means taking the magnitude. So the magnitude of C is going to be the square root of the magnitude of A squared plus the magnitude of B squared. Okay, so in this case, you can see that A is actually just has a length of 4 and B has a length of 3. So 4 squared plus 3 squared, and then you get 5. There. Now, what if I have some arbitrary vector, like let's say AB? So if you look at AB looks like this, right? This is the AB from what we did earlier. So to go from A to B, we need to go -1 in the x direction and 2 in the y direction. So again, you can see this is a right-angled triangle. So the magnitude of AB is actually just 1 squared plus 2 squared. And you take square root of that. So that would be square root of 5. There you go. So that's how you find the magnitude of a vector. So let's say I have some arbitrary vector A, and we have some arbitrary values x, y. The magnitude of A is just going to be x squared plus y squared, and you square root that. Okay? That's all there is to it. So this is all you have done. Oh, actually no, there's something else. There's also something called the unit vector. So the unit vector of A is going to be A divided by the magnitude of A. So what exactly does the unit vector mean? The unit vector is the vector in the same direction as A but with a magnitude of 1. Okay, so suppose I use AB. Let's say I want to find the magnitude unit vector of AB. So the way you write unit vector of AB is usually you would write like this, and then you put a little hat on top to denote that it's the unit vector. Okay, so if you're using like the small letter notation here, you write it as A and then with a hat. Okay, so there you go. So the unit vector of AB, actually you don't have to put the modulus here. You can just put a hat. That's good enough. So the unit vector of AB is going to be AB divided by the magnitude of AB. So what is AB? Well, AB is 1, -1, 2, and divided by magnitude of AB, so 1 over root 5. And that is your unit vector, okay? So just to check that our unit vector has a magnitude of 1, let's try to find the magnitude of the unit vector. So how do I find the magnitude of the unit vector? Well, you can see that the unit vector is actually -1 over root 5 and then 2 over root 5. Okay, so the magnitude of that is just going to be -1 over root 5 squared. plus 2 over root 5 squared, and then you square root the whole thing. So if I square negative 1 over root 5, I'm going to get 1 over 5, and this guy here is going to give me 4 over 5. So if I add them up, I'll get 1. So square root of 1 is 1. So as you can see, the magnitude of a unit vector is always 1. Okay, there you go. What else is there? Let me think. I think that's pretty much it. Yep. So this is all you've done for math in vectors a long time ago. So all of this should be familiar to you, hopefully. So the only thing that we will do is we're going to extend all of this to 3 dimensions, and we're going to introduce the dot product as well. Okay, so first off, let's do the dot product. So I'm just going to move this here. The dot product. So what is the dot product? So let's say I have 2 vectors, A and B. Okay, and they intersect like this, and you can see that they sort of give us some angle theta, right? So if I take A and I dot it with B, I'm going to get the magnitude of A times the magnitude of B times cos theta. So if I rearrange this, I can get cos theta is equals to A dot B over A B, and then theta is equals to arc cos of this thing. So this would allow us to find the angle between 2 vectors, which is kind of the point of doing the dot product, okay, amongst other things, which I'll talk about later. So, why do we use a dot? Why not just put a times? Because for vectors, multiplying and dotting are different things. So multiplying, we usually refer to this as the cross product. Dot, we refer to it as the dot product. So these are 2 different ways of multiplying a vector, and they will give you very different results. So for A2 math, you don't actually learn about the cross product. You only do that in further math, so we can just ignore this one. So how do you actually dot 2 vectors? Well, let's give these vectors some value. So let's say A is 3, 4, and let's say B is 5, 7. Okay, wait, should I use 5, 7? Is 5, 7 a Pythagorean triple? No. What was it again? What was a Pythagorean triple? Oh well, whatever. Doesn't matter. You just make calculations a bit messy, but it's fine. So, if you have A dot B, the way you do that is you put them together like this, and then you take 3 times 5 plus 4 times 7. Okay, so 3 times 5 gives you 15, plus 4 times 7 gives you 28. So that's going to give you 43. So whenever you dot two vectors, you would actually get a scalar. Basically, you end up with a number instead of another vector. If you cross two vectors, you would actually get another vector, but you can only cross three-dimensional vectors, not two-dimensional vectors. But we're not learning about the cross product in A2 math anyway, so you don't have to worry about that. Okay, so that's what happens when you dot these two things. And then you can see this modulus here that refers to the magnitude of the vectors, right? So let's move that here a bit. Let's try to work that out. The magnitude of A is going to be 3 squared plus 4 squared. Square root of that gives me 5. Magnitude of B is 5 squared plus 7 squared. Square root of that is 74. Okay, so theta is going to be arc cos of 43 over 5 times square root of 74. Oh, whoops, hang on. 43 divided by 5 divided by square root of 74. So arc cos of that. Wait a minute, what is going on? 43 divided by 5 divided by square root of 74. The arc cos of that. Okay, yeah. So we get 1.3 degrees. There you go. So that's how you find the angle between two vectors using the dot product. Okay? Now, one interesting thing is if your angle is 90 degrees, so if A and B are perpendicular, then theta would be 90 degrees, correct? Which means cos 90 or cos theta is going to be 0. Therefore, A dot B would be 0 if they're perpendicular. So this is actually one very easy way of checking whether something is perpendicular or not. For example, let's say I have a perfectly horizontal line A and a perfectly vertical line B. So let's say we call A to be 5, 0 and B to be 0, 3. Okay, 5, 0 means you go 5 in the x direction, 0 in the y direction. So these are what we call direction vectors. So if I take A dot B, I'm actually going to get 5, 0, dot that with 0, 3. So 5 times 0 is 0, 0 times 3 is 0, I get 0. Therefore, they are perpendicular. Okay? There's actually something I forgot to mention. So we just go back over here. So if you have a vector that starts from the origin, we call it the position vector, right? However, if you have a vector that does not start from the origin, for example, vector AB here, we call this the direction vector. Because it tells you the direction of AB, right? This direction is -1, 2. You're going this way. Okay. So far so good, because this is pretty much everything there is to know for 2D vectors. Yep, all good. Now we're going to move on to 3D vectors. Thankfully, you don't have to deal with planes because they've actually moved that to further math. So that is usually the hardest part of this chapter, but it's gone now. Oh, excellent. Good for you guys. All right, so now I'm going to move on to 3D vectors. So a three-dimensional vector kind of looks like this. Okay, so basically you have the first one is for the x direction, the second one is for the y direction, and the third one is going to be for the z direction. I can't draw a three-dimensional thing on a two-dimensional piece of canvas, but you're gonna have to imagine that z is going, you know, into the plane. Okay, so A is maybe somewhere here. This is point A, point O, 1, 2, 3. All right. Actually, let me just change this to 3, 4, 5. Okay. Now, how do we find the magnitude of a three-dimensional vector? The answer is you would take 3 squared plus 4 squared plus 5 squared. What actually is happening here is you're doing a double, you're doing Pythagorean theorem twice. So this is going to be a bit tricky to explain, but I'll try my best. Okay, so let's say this looks like that. Okay, you can imagine this kind of goes like this. So from here to here, it's 3. From here to here is 5. From here to here is 4. And if you look real closely, you see that this is actually a 90-degree angle. This is a right-angled triangle. This is another right-angled triangle. So if you want to find the vector A, we need to find this blue line first, the length of this blue line. So the length of the blue line, we'll call it B. Okay, so B is going to be 3 squared plus 5 squared. Square root of that. So now to find A, we can do Pythagoras, the Pythagorean theorem again. So that would be B. Hang on, I forgot to put a magnitude here. So to find the magnitude of A, I have to take the magnitude of B squared plus 4 squared, and then square root that. So if I square the magnitude of B, I just end up with 3 squared plus 5 squared plus 4 squared, which is actually this guy. So as you can see, we're doing the Pythagorean theorem twice, okay, which essentially simplifies to this. So whenever you want to find the magnitude of something, and let's say that something has coordinates x, y, z, or you know, vectors x, y, z, all you got to do is take the square root of the square of the sum of the squares, like that. Okay, and that's it. Next, we're going to try to find the unit vector of a three-dimensional vector. So the unit vector of A, we're going to take 3, 4, 5 as our previous example here. The unit vector of A, again, is the same thing. Is you take the vector A, divide by the magnitude of the vector A. So the magnitude of our vector A, what's that going to be? Well, let's see. 3 squared plus 4 squared plus 5 squared, and the square root of that is 5 root 2. So this guy actually gives us 5 root 2. Okay, so 1 over 5 root 2 And then A here is going to be 3, 4, 5. And that is our unit vector for A. Done. Right. What else is there? Yes, the dot product of two three-dimensional vectors. So let's say we have another vector, we call it B. Let's say this vector B is 0, 1, 1, just to make things easier. So what is the angle between A and B? So remember, okay, so this is something that I have to draw your attention to. If I have two vectors A and B, and I take the dot product of these two vectors, I will always find this vector here. Okay? But if the question wants you to find this vector, phi, you have to take, so phi is actually 180 degrees minus theta. So whatever angle that you get from the dot product, it's going to be the angle that is sandwiched by the two vectors. So if you want to find the other vector, you have to use this relation. Okay, so it's something very important to take note of. Okay. By the way, I should point out that this angle is the same as this angle because of the geometry of it. Okay, so if I want to find A dot B, the dot product, again, I'll just use the same dot product formula. Okay, so what is A dot B? Well, A dot B is going to be 3, 4, 5 dot 1, 1, 0, which is going to give me 3. Sorry, what am I doing? What am I doing? Which is going to give me 3 times 1 plus 4 times 1 plus 5 times 0, and I'll get 7. And then the magnitude of A, we worked that out already, is 5 root 2. The magnitude of B is going to be 1 squared plus 1 squared plus 0 squared, which is square root of 2. Cool. So cos theta is going to be A dot B over magnitude of A times magnitude of B. That'd be 7 over 5 times 5 root 2 times root 2, which is 10. So I get 7 over 10, which is 0.7. So theta is arc cos of 0.7. Which is 45.6 degrees. There you go. That's it. Okay. Now, we're going to move on to what happens when you have two lines. Oh, actually, before we do that, something very important. I need to show you the vector equation of a three-dimensional line. Okay, I'm going to move that here. So far, you know what a Cartesian equation looks like. The Cartesian equation of a line looks like this. Y equals mx plus c, right? So next, I'm going to show you what a vector equation looks like. So for a two-dimensional plane, let's say I have a two-dimensional plane like this. And I have a line that looks like that. Okay? So this line passes through 2 points. It passes through point A and point B. So point A is going to be, let's say 1, 2. Point B is going to be 2, 3. All right? So this line extends in both directions, and it sort of goes on forever. It's an infinitely long line. It's not like the AB over here. This AB is a finite line, okay? But this is an infinitely long line that stretches in both directions. So how do I express this line? Well, you need two things. The first thing is you need a position vector on the line. The position vector of a point on the line. So it can be A or B. So you can choose either A or B. So you choose one of them. Eight BV. Okay, yep. I've gotten some questions from you guys, so I will discuss those questions once we are done with vectors. If you guys have any other questions you want me to discuss, today is your last chance to send them to me. All right, so anyway, the second thing you have to do is you need to find the direction vector. Find the direction vector
Hydrate or
of
I'll
the
slap your
line.
pancake.
So the direction vector here is just AB. Okay, so what is AB? AB is AO plus OB, and AO is negative OA. So OA is 1, 2. OB is 2, 3. So what do we get? Negative 1 plus 2 is 1. Negative 2 plus 3 is 1. So direction vector is 1, 1. Okay, so now we're done. So now for our last step, we write our vector equation. And the vector equation always looks like this. R is equals to our position vector. So our position vector, let's put OA. So that would be 1, 2. Sorry, I should put an OA over here. It'll be like that. Okay. And then we're gonna put plus here, and we're gonna put lambda, and then the direction vector goes here. So this guy is always the position vector. Any position vector on the line. And this guy is going to be the direction vector. So this actually represents every single point on the line, and this R here, this R actually represents an arbitrary point on the line. And this lambda here is what we refer to as a parameter. Lambda here is any real number. For example, if I want to pick this point here, this point is maybe, okay, you know what, maybe I'll pick this point. Let's say I want to pick this point here. This point is actually 3, 4, okay? So when lambda is equals to 1, is equals to 2, then R is equals to 1, 2 plus 2 times 1, 1, which is going to give me 3, 4. Okay, when lambda is equals to 0, R is going to be 1, 2, which gives us OA back. When lambda is equals to 1, R is equals to 2, 3. Lambda can also be 0.5. Lambda can also be 1 over 3. Lambda can basically be any real number. Okay, so if you put all the real numbers into lambda, you would actually trace out a line that goes infinitely in this direction and infinitely in this direction. That's why this equation represents your vector equation of the entire line. Okay, does that make sense? Ooh, hydrate. Very well. I shall drink some water. You guys should drink some water too. Thanks for the hydrate, the orange trader. Ooh, okay. um, you know what? let's go through this question real quick. Question 8b. Part 5. What do you mean? Question 1, part 5? I'm guessing it's question 1, part 5. So exercise 8b, question 1, part 5. So integrate x square root of 2x plus 1 dx. And the suggested substitution is 2x plus 1, which means du dx is 2. So dx is equals to 1/2 du. Okay, so this becomes x square root of u 1/2 du. But you can see there's an x over here. So what you got to do is, you can see that 2x plus 1 is u, right? So from here you can see that if I make x the subject, I will get u minus 1/2. So this is actually u minus 1/2 square root of u, and then there's a 1/2 here. So I'm going to take out both 1/2, so I have 1/4 out here. U minus 1 square root of u du. And then I'm going to multiply the u inside, so I'm going to get u1 times u half gives me u3/2. This would be u1/2. And then I integrate normally, which gives me u5/2 over 5/2 minus u3/2 over 3/2. That's a plus c. And then you simplify, and that's your answer. There you go. Okay, let's see, any other questions? Nope. Okay. Right, let's talk about the vector equation of a three-dimensional vector. All right, same thing, you're just doing this equation here. However, there's something else that we have to add in as well. Well, actually, no. Okay, so for a three-dimensional vector, it's still going to look like this. It's going to be r equals to some position vector plus lambda and then some direction vector. Okay? But in, let's say our position vector is 1, 1, 0, and our direction vector is 2, 3, 4. Then it just looks like this. Okay, so that's pretty much the only difference between a two-dimensional vector equation and a three-dimensional vector equation. You just have more elements in the matrix. That's it. Okay. What else is there? Okay, so sometimes in the exam, they would give you two vector equations. And then they would ask you whether these lines intersect or they do not intersect, right? So let's say you have two lines, but these lines are in 3 dimensions. So these lines could be intersecting, which means they look like this, okay? Or, let me just make the screen a bit bigger. So let's say you have two lines. They could be intersecting like that, or they could be skew, which means they look like this. They do not intersect. Okay. Another thing that could happen is they could be parallel. So they are both like this. Parallel lines. So you have three things that could happen. For three-dimensional vectors, you could have 3D vectors or lines can either intersect, skew, or be parallel. So how do you check if two lines are parallel? Well, if they are parallel, then the direction vectors would be a scalar multiple of one another. So direction vectors will be a scalar multiple of one another. So what that means is, let's say I have a vector equation of a line. Let's say we call it 1, 1, 0. We call this R1 plus lambda 2, 3, 4. And then I have another equation. We call it R2. Let's say this is 2, 0, 4 plus mu 4, 6, 8. Okay, so these are two different lines. So if you look at the direction vectors, so direction vectors refer to these these matrices here, not these ones. These ones are just points on the line, position vectors on the line. These are the direction vectors, okay? So if you look at these two direction vectors, you see that 2, 3, 4 is actually half of 4, 6, 8. So this is a scalar. So you can see this is actually a scalar multiple of one another. So if you can write the direction vector like this, so let's say this guy is A, this guy is B. So if A is equals to KB, where K is some real number, then R1 is parallel to R2. Okay, that's how you check whether something is parallel or not. Now, what about intersection and skew? Okay, so this one I have to use an example to show you what's happening. Where is it? Aha. Okay, is it this one? Yes. Okay. So let's say we have R1 equals to 1, 2 minus 1 plus lambda 2 minus 3, 4. And then we have another one, R2 is 4 minus 2 minus 5 plus mu minus 1, 2, 1. Okay. So the question is, are these lines intersecting, skew, or parallel? So first thing is you check whether they're parallel. So if you look at the two direction vectors, 2, minus 3, 4, and minus 1, 2, 1, can you actually put a value of k such that the left side becomes equals to the right side? The answer is no, you can't, right? Just by looking at it, you know you can't. So therefore, we know it is not parallel. What about whether they intersect or not? So if they intersect, they should share the same point, correct? Which means if, okay, let me just write here, if they intersect, then at some point, R1 must be equals to R2, correct? So we're going to try to equate them together and see whether we can get, we can find that point. So we're going to have this guy plus lambda 2 minus 3, 4. It's going to be equals to 4 minus 2 minus 5 plus mu negative 1 to 1. Okay, I'm going to equate them together. So that's going to be 2 lambda 2 minus 3 lambda minus 1 plus 4 lambda equals to 4 minus lambda, 4 minus mu, sorry, minus 2 plus 2 mu, minus 5 plus mu. Okay, as you can see, we actually end up with 3 different equations. So our first equation is this guy here. And we're gonna try to simplify this a bit first. Hang on. Let's simplify this a bit. So that's gonna give me 2 lambda equals to 3 minus mu. Okay, we'll call this our first equation. Our second equation is this guy here. I'm going to move that over here. So we get 4 minus 3 lambda equals to 2 mu. So our second equation. And our third equation, we have this guy equals to minus 5 plus mu. Then I simplify this by moving all the numbers to one side. We call this 3. Okay, so let's try to solve this simultaneously. So if you see here, we actually have 2 unknowns, but 3 equations. So we actually only need to choose 2 equations, because if you have n equations, if you have n unknowns, sorry, you just need n equations to solve them. So if I have 3 unknowns, I need 3 equations. If I have 4 unknowns, I need 4 equations. In this case, I have 2 unknowns, so I only need to choose 2 equations. Okay, so I'm going to choose, let's say, 1 and 2 here, 1 and 3. So I'm going to take 3. I'm going to add that with 1. So we have 4 plus 6 lambda, and then we have 3, and then mu plus negative mu disappears. So we have 6 lambda equals to minus 1, lambda equals to negative 1 over 6. Okay, so if lambda is negative 1 over 6, what is mu going to be? Well, that's going to be negative 1 over 3 minus 3, and then the whole thing times by minus 1. So what's that? 10 over 3. Okay, so you're not done yet. So once you have found lambda and mu, what you need to do next is you need to put these 2 values that you've found of lambda and mu into the remaining equation that you didn't use to solve simultaneously with. Okay, so you have to take this guy, you take this guy, and you're gonna chuck them into this guy over here. Now, if the left hand side is equals to the right hand side, so this is a solution of this equation. So if this is a solution of this equation, that means the lines intersect. If they do not work, right, if the left hand side does not equals to the right hand side, then they do not intersect, which means they are skew. Okay, so let's see, left hand side, what do we have? We have 4 minus 3, 10 over 3. What is that going to give us? 4 minus 10 is negative 6. Okay, right hand side, what do we have? 2 mu. Sorry, I messed up. Oh no, I messed up. Hang on. This one is negative 1 over 6, which means it's plus, so 4 plus a half, 4.5. Okay. So this one is 2 times 10 over 3. What do we get? We get 20 over 3. As you can see, the left-hand side is not equals to the right-hand side. So since they are not equals, therefore, the lines are skew, which means they look like this. They do not intersect. Okay? There you go. So that's how you check whether a line is intersect, skew, or parallel. So you can actually try exercise 10E for this one if you want to practice this part. So 10E, question 1 and 2. You don't have to do the rest actually. Question 1 and question 2. For two-dimensional vectors, you will never get a skew. So for two-dimensional vectors, it's only intersect or parallel, because you can't have two lines that are skew in 2 dimensions because you only have 2 dimensions, right? But yeah, anyway, if you want to practice this, you can try this part in your textbook. Okay. Ooh. So I realize we're going really fast because it's our last class, so I'm just covering the things that you need to know, and we're just doing just a few very simple examples. But yeah, anyway, there's actually one last thing I have to show you before we are done with this chapter. So do you guys have any other questions? Feel free to send them to me. Okay, so one last thing that you have to know for vectors, let me just move that over here, is how to find the distance between a point and a line. So usually this is in 3 dimensions, right? So the shortest distance between a point and a line in 3D. So the shortest distance is going to be the distance where if you were to draw a line from the point to this line that we are interested in, it's going to be 90 degrees. And we need to find the distance of this red line over here. So we're going to call this point A. Okay, and then this guy here, let's say we have some, okay, so this we'll call it R. So this R has some, we're going to put in some numbers. So let's say this is 101 plus lambda 120, okay? And then A here has some coordinate 2, 3, 0. 2, 3, 0. Let's put 2, 3, 2, 3, 5. Yep, okay. So find the shortest distance between A and this line. Okay, the first thing you got to do here is you need to assign an unknown to this this point over here. We'll call it n. Okay. So if this is perpendicular, so you can see that this line is perpendicular to this one. So if this is perpendicular to this line, that means the dot product of an with the direction vector of the line, which is 1, 2, 0, is going to be equals to 0, correct? Because the dot product is equals to the magnitude of this times the magnitude of this times cos theta. But if theta is 90 degrees, cos theta is 0, which means the dot product must be 0, right? We talked about this earlier. So first we need to find an expression for an. Okay, so how do we do that? Well, n is actually a point on this line. And R here represents all the points on the line. So we're going to say that if lambda is equals to k, because lambda can represent any real number, so we're going to put in k. K is going to be one of the real numbers, because lambda is all real numbers, right? K is going to represent only one real number. So if lambda is equals to k, then R is going to be equals to ON, because we need to find the position vector of n. So ON is going to be equals to 1, 0, 1 plus k, 1, 2, 0. So simplifying this, I'm going to get 1 plus k, 2k, and then 1. All right? So we've actually found a position vector for n in terms of k. So this is good, because now we can find an. So an is actually AO plus ON. AO is negative OA. And we know what OA is. OA is actually 235. ON is 1 plus k, 2k, and 1. So adding these up, we're going to get negative 2 plus 1 is negative 1, so k minus 1. Negative 3 plus 2k gives me 2k minus 3. And then negative 5 plus 1 gives me negative 4. So we have actually found an. Okay? There we go. So, thinking we said, we're going to chuck that in there. We get k minus 1, 2k minus 3, negative 4. Dot that with 1, 2, 0 equals to 0. So now we're going to do the dot product. So k minus 1 times 1 plus 2k minus 3 times 2 plus negative 4 times 0 equals 0. Expanding this, we get k minus 1 plus 4k minus 6 equals 0. So as you can see, we can actually work out what k is. K is 7 over 5. Woohoo! So once we've found what k is, we can actually work out what the distance an is, because an, the magnitude of an is what we are ultimately looking for. So the magnitude of an is going to be the square root of k minus 1 squared plus 2k minus 3 squared plus negative 4 squared, right? And we know what k is, so we can just substitute that in here. And you just put that into the calculator. So square root of that gives me 4.025. There we go. We've found the shortest distance between the point and the line. And done. There we go. If the shortest distance is 0, that means the point is on the line itself, which means you probably did something wrong. So one thing that I have to point out that you have to be careful with is when you take the dot product of this one, you should take an and you dot it with this and only this. You don't dot it with this guy here. Okay, you dot it with the direction vector, not the position vector. So that is the important part that that students tend to mess up. Okay, sometimes they just take the whole thing and dot it with this, and you get like an unknown with lambda in it. That's not what you're supposed to do. So that's it. That is pretty much everything there is to know when it comes to vectors. So do you guys have any last minute questions that you want to ask me? Because this is our last class. Okay, so the exercises that you can attempt on the textbook, you can do 10F. Let's see. 10F, you can actually do all these questions. So 10F, that's fine. You can do all of them. And D. And C, that's doable as well. A vector is a special type of matrix, or a matrix is a collection of vectors. Vectors are a special type of matrix. Yeah. So Well, actually, both statements are true. Matrices are also a collection of vectors. Well, specifically, let's say sometimes you see matrices that look like this, right? Let's say you draw 1, 2, 3, 4, 5, 6, 7, 8. So this is actually a collection of matrices, a collection of vectors, and the vectors look like this. Yeah. But sometimes instead of writing multiple points, so usually these represent different position vectors on your Cartesian plane. So 1, 2 could be here, and then maybe 3, 4 is here, and then 5, 6 is maybe here, 7, 8 is maybe here, right? So sometimes if you want to see what happens when you multiply, when you subject all these vectors to some transformation, so the transformation is usually a 2 by 2 matrix. So if you put a transformation like this and you put all these points, so these points could maybe connect to form like a shape, right? So the shape maybe looks like this. So if you subject all these points to a transformation matrix, you would actually get like a, you know, an enlargement. So everything would get enlarged by 3 times. So it becomes something like this. And the way you calculate that quickly is by grouping them together into a collection of vectors like this, which look like a gigantic matrix. So yeah, both statements are actually correct. However, matrices, not all matrices are vectors, but all vectors are matrices. So kind of like vectors are a subset of matrices. Yep. Good question. Okay, so anyway, you can actually try all the questions here from 10A to 10F. I'll just write that here. You can try 10A to 10F if you want to have a little warm-up session. But for 10D, you only have to do question 1. Was it 10D? I think it was 10E, right? Yeah, so there was one part, yeah, this one, 10E. So 10E, just do 1 and 2. You can ignore the rest. The rest are not really important. But the rest you can actually do every single question. But if you're feeling adventurous, or if you've done further math already, you can just jump straight to the past year questions. Okay, I'll post the past year questions on Google Classroom in a bit, and you can download it from there. I will also post the past year questions for complex numbers. That's the following chapter, which I will not go through with you because next year, Mr. Zikri is going to take over. Well, next year meaning September, not 2022, but yeah, 2021 September, Mr. Zikri is going to take over, and he'll continue from there. So I'll let him know that you guys have actually stopped at vectors. But if you want him to go through vectors again or any of the previous chapters, just let him know, okay? Because I realized that I've been going through this very quickly. So yeah, if you ever want to go through these again, just let him know. And I'm going to sort of export all these videos to YouTube so you can rewatch them at any point if you want to. Okay, so that's it for today, and that's it for this term. It's been a pleasure teaching you guys. I hope you guys, you know, do well in your exams. And yeah, all the best in your future endeavors. Good luck and all that. I'm not very good with farewell, so going to the topic quickly and having a lot of time revision. That doesn't sound like a bad combo. No, true. Yeah. So ideally, we will finish the syllabus by March. So I've actually told this to Mr. Zikri already. So uh, ideally, we would finish the syllabus by the end of March or the mid of March, because in April you would be sitting for your mock exam. Well, actually, the end of March you're sitting for the mock exam, and then the beginning of April you would be done with your mock exam, which means you would have the rest of April, so probably 2 weeks, 3 weeks ideally, and then May you would sit for your A2 exam. So you have about 3 weeks of doing past years and revising. But again, I think you should start doing the topicals now, because the topicals only cover up to 2019. So even if you finish all the questions on the topicals, you still have plenty of past years to go through from 2020 and 2021. So there won't be a shortage of questions. And if you try to do all that in the 3 weeks and you're taking 4 subjects, you're not going to finish in time. So you should start now if you can. Okay, anyway, enough yammering from me. I will maybe see you guys again one day. Keep in touch. Good luck and goodbye. For those taking physics, I will see you tomorrow for our last class. For those not taking physics, this is farewell. Bye bye.
Hydrate or slap your pancake.